Imagine you are standing in a sprawling, unfamiliar city. You have a map. It's a labyrinth of streets, one-way alleys, bustling squares. Your goal is simple: from home to the Central Park. You want the fastest route, not just any route. You could wander aimlessly, but that would be inefficient. You could try every possible path, but you'd be walking until nightfall. What you need is a strategy that intelligently guides your choices. A system that prioritizes promising avenues and avoids dead ends. This is a core challenge in computer science, robotics, and AI. Enter the A-star search algorithm. A-star, is not just another pathfinding method. It is an exceptionally clever one. It finds the shortest path between two nodes in a graph. It combines two ideas: actual cost of the path traveled so far, an educated guess, the heuristic. To understand A-star, we first need a landscape to navigate. In computer science, we model landscapes like cities and road networks using a structure called a graph. A graph consists of nodes, or vertices, which represent locations, and edges, which represent the connections or paths between those locations. For a pathfinding problem, these edges usually have a weight or a cost associated with them. This cost could represent distance, travel time, fuel consumption, or any other metric we want to minimize. Our goal is to find a sequence of connected edges from a start node to a goal node such that the sum of their costs is as low as possible. Let's build a small, concrete example to work with. Imagine 5 cities: A, B, C, D, E. These are our nodes. They are connected by roads, which are our edges, each with a specific travel cost. The road from A to B costs 2 units. From A to C, the cost is 4. From B to C, it is a cheap 1 unit. From B to D, it's 7. From C to D, 2. From C to E, 5. And from D to E, 1. Our journey will start at node A, and we want the cheapest way to get to node E. Now we add the secret ingredient of A-star, the heuristic. A heuristic, h of n, is an estimated cost from any given node n to the goal. For our graph, HA cheers 6, HB cheers 4, HC 3, HD cheers 1, and HE cheers 0. With our graph and heuristics in place, let's watch A-star work its magic. The algorithm maintains 2 lists of nodes: open set and closed set. The open set contains all nodes that have been discovered but not yet fully explored, your potential next steps. The closed set contains nodes that have been fully explored, every neighbor considered. We won't consider them again unless a much better path is found. A-star begins by placing A into open. We compute an F value to guide decisions. Initially, FA6. With A the only option, we select it and move it to closed. Now we look at its neighbors, B and C. The path to B costs 2, so GB 2 and FB 6. The path to C costs 4, so GC 4 and FC 7. We pick the lowest F value, B, move B to closed and examine its neighbors, C and D. Through B, ABC costs 2 plus 1, 1, 3, better than 4, so update C, G or 3, F to 6. We also discover D through B, G9, F10. Pick C next. Move C to closed and inspect D and E. Update D to G5, F to 6. Discover E via C, G8, F to 8. Visit D, update E to G6, F to 6. E is lowest, goal reached. Section 4, the magic ingredients. Defining G, H, and F. The algorithm's intelligence is encapsulated in F of n equals G of n plus H of n. Gn is the actual cost from start to n. It's not an estimate, it's the sum of edge weights along the best known path so far. At start, GA0. After AB, GB2. With ABC, GC3. HN is a best guess cost from n to the goal, an optimistic estimate that guides the search. For example, HB4 told A that from B, there were roughly 4 units to go. Fn combines the known past with the predicted future, the estimated total if the path goes through n. By choosing the lowest F, A balances exploration and exploitation, aiming at the overall cheapest path. This simple equation lets A navigate complex graphs with surprising efficiency. Section 5 Neuron, the guarantee of greatness, admissible heuristics and optimality. We have seen that A finds a path, but how do we know it finds the best path? The guarantee hinges on one property, admissibility. A heuristic is admissible if it never overestimates the true cost to the goal. Straight-line distance is a valid lower bound for road travel, optimistic but not excessive. Overestimates can cause A to avoid optimal routes. With admissible H, FG plus H is a lower bound on the true best path cost. When the goal has the lowest F, any better path would have even lower F and would have been explored first. Therefore, the found path is optimal. Stronger. Consistency, monotonicity, requires HA, gauge cost, AB, plus HB for adjacent nodes. Consistency implies admissibility and ensures optimal paths to closed nodes, improving efficiency. For most practical use, design a consistent heuristic. Section 6. A in the real world, from games to GPS. Games use grids or navigation meshes. A computes movement quickly in real time. G is distance traveled. H is typically Euclidean or Manhattan on grids. Efficient A avoids bizarre routes and performance hits. Robots and autonomous systems plan safe, efficient trajectories with A. Edge cost can include terrain difficulty, fuel consumption, and hazard avoidance. Heuristics prune nonsense paths and focus the search on viable routes. GPS services solve massive shortest path problems with A-like methods. They combine known travel time with estimated remaining time to find the best route. Section 7. The enduring power of a smart guess. A solves shortest paths with guidance, not brute force. It balances the known past, GN, with an optimistic future, HN, to hone in on the optimum. It maintains open and closed, always pursuing the lowest F. Optimality comes with an admissible heuristic. Never overestimate, and A guarantees the shortest path. This power underpins games, navigation, logistics, and robotics. Pro tip: invest in the heuristic, close to true cost, never overestimating, and cheap to compute. In the end, a smart guess can be the most direct path to the right answer.